Alright, in this video we're going to talk about the force of gravity. And we've talked a lot about the force of gravity in physics so far, but in this video we're going to introduce another equation to find the force of gravity, and it's known as Newton's law of universal gravitation. And I wanted to point out a couple of things with this new equation. And so force of gravity, if we put a little sub g here, force of gravity is equal to big G, which is the universal gravitational constant. It's a number, and it equals, so let me put down what it equals, 6.67 times 10 to the minus 11. And you times g by mass of one of the objects, times by the mass of the other object, and you divide it by the distance between them squared. And so I wanted to point out a couple of things with this new force of gravity equation. One that I think is probably maybe most important is that anything in the universe with mass will have a force of gravity associated with it, even if its mass is very small. And another thing that I wanted to point out was that the force of gravity follows this inverse square law with regards to the distance between the two objects. And so we're going to see that a lot. Another thing that I wanted to kind of go over with this equation that you should recognize is that as the mass gets larger, so as mass increases, what happens to the force of gravity? So if this number right here was to get bigger, what would happen to the force of gravity? Well, it would go up. And so if mass gets bigger, so does the force of gravity. Well, what if mass gets smaller? So what if this number right here decreases? Its mass decreases. Well, if mass decreases, the force of gravity will decrease. And so you'll see a smaller force of gravity for smaller objects. Another thing to point out, and what's happening with this inverse square law with regards to distance between the objects, is what would happen if the distance between the objects, so distance, what if distance was to increase? And so now this number becomes larger. Well, because we're dividing by a larger number, force of gravity is going to go down. So if distance increases between them, you're going to see the force of gravity between them go down. And just the opposite, if the distance between these objects gets smaller, so it decreases the distance, so they get closer together, now we're dividing by a smaller number, which will make the force of gravity go up. And so as two objects get closer together, you're going to notice that the force of gravity becomes larger. Anyway, let's go through a couple of practice problems dealing with this new equation, this new Newton's law of universal gravitation, to show you how to solve for force of gravity using it. Okay, in this first problem it says, find the force of gravity between two physics students that have the masses of 65 kgs and 80 kgs if they are sitting 1.2 meters apart. Okay, I always like to draw a picture of what's going on. So here's one of the students, and we'll say this is the student that weighs 65 kgs. Okay, and they're sitting 1.2 meters apart. So here's our other physics student who weighs, or has the mass of 80 kgs, excuse me, mass of 80 kgs. Okay, and the distance between them was 1.2 meters. Alright, now we're going to use Newton's law of universal gravitation to solve for the force of gravity that exists between them. And so if we remember that equation, the force of gravity is equal to G m1 m2 all over the distance between them squared. So I'm just going to plug in these numbers now. G, I will always give you the universal gravitational constant is this number. And so I'm just going to plug them in right here. 6.67 times 10 to the minus 11th. And the units for for it to work out are in Newton meter squared per kilogram squared. And the kilogram will be on the bottom to get it to give you newtons in the end. I'm going to leave off the units just for the sake of space here. M1, it doesn't matter which order you put them in. I'm going to put 65. And then for M2, I'm going to put 80 kgs. 80 kgs. And then you divide that all by the distance between them squared. And this has to be in meters to get the units to work out. And luckily in the problem it was 1.2 meters apart. So 1.2, but don't forget that the distance between them is squared. Okay. And now everything's finished except for the math. Let me put that in my calculator. So 6.67 e to the minus 11 times 65 times 80. And then we're going to divide that number by 1.2 squared. And so the force of gravity that exists between these two physics students, I'm finding it to be 2.41 times 10 to the minus 7th. And units for force is always going to be in newtons. And so I'll put newtons there. And so you might want to look at this number and ask yourself, is this a very large force? And it's times 10 to the minus 7th, so it's a very, very small force. And that's due to the fact that the mass of these two students, is pretty small. And so you'll see force of gravity will go up if we're using more massive objects. But and that's also a good thing to point out. You don't feel the force of gravity between you and another person that's nearby, because if you compare this force of gravity to the force of gravity between you and the Earth, this force of gravity is very, very small. So it's almost minuscule. So anyway, that's how you use the equation. Just plug in the numbers and find your new force of gravity. Let's try another one. Okay, here on the second problem, it says find the force of gravity between you and the Earth. You have the mass of 65 kgs, and the Earth's mass is 5.98 times 10 to the 24th kgs. The distance between you and the Earth, and we have to measure to the center of the Earth, which is also the Earth's radius, is 6.38 times 10 to the 6th meters. And that brings another important point. We always measure the distance between two objects between their center of mass. And so we have to measure from the Earth's the center of the Earth, the Earth's core, to the outside where you're standing. That would be the Earth's radius. Okay, so let me write that. Well, let's draw a picture first, okay? So there's the Earth, and here's you standing on the Earth. Obviously not to scale, but the distance between you and the Earth will be the radius of the Earth. So radius of the Earth. Okay. You had the mass of 65 kgs. And the Earth had the mass of 5.98 times 10 to the 24th kgs. Okay. And now we can use Newton's force of gravity equation. So force of gravity is equal to G, M1, M2, all over the distance between the two objects squared. Now I'll just plug in those numbers. G, I didn't give it to you here, but I always will in the problem. So 6.67 times 10 to the minus 11th. Okay, that's what G equals. M1, let's just say the mass of U is 65 kgs. Okay. And the mass of the Earth, 5.98 times 10 to the 24th kgs. And we have to divide that all by the distance between them squared. The distance between you and the center of the Earth we'll call the Earth's radius. which is 5.9. Oh no, sorry. The Earth's radius is 6. Let me change this. It says 6. So this is the Earth's radius, 6.38 times 10 to the 6th meters. And don't forget that the distance between them has to be squared. So let me put that in my calculator, and you should do the same and see if you can get the same number as me. 6.67 times 10 to the minus 11th times 65 times 5.98 times 10 to the 24th, and we're dividing that number by 6.38 or times 10 to the 6th, but it's got to be squared. Okay, and so I'm getting that the force of gravity, so force of gravity between you and the Earth is going to be equal to 630, if you round it to the nearest whole number, 637. And remember, the units for force is always newtons. And so that will be your answer. Okay. And this is a good place to bring up the fact that we've talked about the force of gravity between you and the Earth all year. And you know, if you remember us doing free body diagrams of, if you were to draw the free body diagram of you, you would have this arrow going down, and we always put force of gravity is equal to m, which is the mass of you, times g, which is the acceleration due to gravity. And so let's just quickly back this up and see if we can get the same answer. So the mass of you was 65 kgs. Okay, and we're going to, so I'm just plugging the numbers in here, times that by the acceleration due to gravity, which is 9.8 meters per second squared. And so let's do that on my calculator. 65 times 9.8 is exactly 637 newtons. And so you should notice that it doesn't matter which equation you use, the force of gravity between you and the Earth is the same. And another important point to point out, the force of gravity is equal to mg. That's what we've learned all year. In a lot of physics textbooks, you'll see it written as weight is equal to mg, because your weight is the force of gravity, the force that's pulling you down toward the Earth, and that's what your weight is. And so you'll see it both ways, written in textbooks that way. So anyway, I just kind of wanted to show you that even though we're using a new equation, this Newton's universal law of gravity, it does work the same way as the one we've used in the past. Okay, on this final example problem that we'll go through, it says on number 3, calculate the acceleration due to gravity on Earth using the two force of gravity equations that we've learned so far. Okay, and let me write down what the two force of gravity equations we've learned. The first one that we've spent most of the year learning with our free body diagrams is that the force of gravity is equal to the mass of u times the acceleration due to gravity, which is just g. Force of gravity is equal to mg. This new equation that we've learned is also the force of gravity, but now we times it by g, okay, times the mass of u times, if we're doing it between you and the Earth, okay, so let's draw a picture again. Here's you on the Earth, and so the mass of the other object would be the mass of the Earth, mass sub Earth, divided by the distance between you, which would be the Earth's radius squared, so distance squared. And so if you look at this, force of gravity is equal to this term here, and this force of gravity is equal to this term. Well, if force of gravity is equal to both of them, we can set these two terms equal to each other. And that's, if you remember this logic here, if A is equal to B and B is equal to C, there's one more relationship we know in this one, and that means that A has to equal C. And so again, if the force of gravity is equal these two terms have to equal each other. And so what happens when we set them equal to each other? And we get this mass of u times the acceleration due to gravity is equal to g times the mass of u times the mass of the Earth all over the distance between you squared. Now, in the problem we're supposed to solve, it says calculate the acceleration due to gravity. And so that's what we're supposed to be finding. And so what I'm going to do is divide this side. To get g by itself, I'm going to divide it by mass of u, and divide this side by mass of u. Okay, and you're going to notice that on this side mass of u cancels out, and on this side mass of u cancels out. And so if you rewrite this equation, let me rewrite it over here, you're going to be left with g is equal to big G, which is the constant, times the mass of the Earth all over the distance between you and the Earth squared, which is the Earth's radius, so distance squared. And if we plug in these numbers, g will be, let's see, let me just write it real quickly, 6.67 e to the minus 11th. We're going to times that by the mass of the Earth, and the mass of the Earth we gave you up there, which was 5.98 times 10 to the 24th, and divide that by the distance squared, which is the Earth's radius, so 6.38 times 10 to the 6th, but we got to square it. Okay, I'm going to punch these numbers into my calculator real fast, but we can make a prediction before we do. G had better be something close to 9.8, because that's the number we have been using all year. And so 6.67 e to the minus 11th times 5.98 e to the 24th equals, and then divide it by the distance between them squared, so the Earth's radius squared, 6.38 e to the 6th squared. And my calculator is giving me 9.799. So again, we just kind of reinforced this idea that the acceleration due to gravity is equal to 9.8, and if we put the units on there, it would be meters per second squared. Anyway, kind of a interesting calculation to show how you can find the acceleration due to gravity, and you can do this in any planet or any place in the universe, and it would work. Okay, so hopefully that helps you get used to this new equation for gravity. What I've got for you on your video physics assignment this time is 2 questions that will be very similar to the questions that I just went over. And so again, if you have troubles, if you get a little bit confused, go back, rewind through the video and watch it one more time or two. But if you still are confused, still get stuck, please feel free to come by anytime and I'll help you and we'll get it solved. But we'll scroll through the next 2 questions very slowly so you have time to write them down, and good luck.